NASA found a planet candidate called HD 137010b orbiting a star known as HD 137010, located about 146 light-years from Earth. It shares some key similarities with our planet, and scientists consider it one of the more promising candidates to study in the search for life. This is a planet we can actually study with current and near-future technology. This is about a discovery that happened recently, one that scientists are studying closely to learn more about where life might exist beyond our own pale blue dot. Here's what makes this so different. Most planets we find are either scorching hot gas giants or cold, rocky planets far from any warmth. But this one, it shares several key characteristics with Earth that make it stand out from most planets found so far. Early data suggests the planet may be similar to Earth in size, with an orbital period that places it at a potentially suitable distance from its star. The star it orbits is slightly cooler and dimmer than our Sun, but belongs to a stable, long-lived class of stars that have been shining steadily for billions of years, long enough for planets to form and develop. And the location? Its position right where astronomers have been hoping to find something special for decades. Researchers noticed a pattern in the data, a repeating dip in starlight that suggested something worth investigating further. That's what happened here. The team reviewing telescope data noticed a dip in starlight from the star HD 137010, a stable, long-lived star somewhat cooler than our Sun. Not a quick flicker from a small planet zipping close to its star, not the deep plunge of a massive gas giant. This was different. The timing suggested something further out, something in a longer orbit, something that took its time crossing in front of the star. When they ran the calculations, the numbers lined up with what we've always imagined an Earth-like world might look like from far away. But here's the thing about planet hunting. One shadow isn't enough. You need confirmation. You need to see that same dip happen again, proving the planet completes its orbit and passes in front of the star on a regular schedule. The signal is strong, consistent, and detailed enough that scientists are already treating it as a priority target for follow-up study. What gets people excited isn't just that this planet might be rocky or might have the right size, it's the combination. When you add up the star type, the orbital distance, the estimated mass, and the potential for an atmosphere, you get a profile that resembles Earth more closely than most planets found so far. Finding a planet with this combination of features is rare enough that scientists are taking a very close look, and that's where we are right now. This discovery may shift how scientists think about where life beyond Earth could exist, not because this planet guarantees life exists there, but because it shows us that worlds like ours, worlds with the right ingredients, the right conditions, the right neighborhood, are out there waiting to be studied. And this one? It's close enough and bright enough that we won't have to wait centuries to learn more. If this video gave you something to think about, or helps more people find it, subscribe and turn on notifications so you don't miss the follow-up when new data comes in on this planet, and drop a comment with your biggest question about this discovery. I read them all. Now let's dig into the details. How exactly did they find this planet? What clues did they follow? And why does this discovery feel different from all the others? Finding planets around distant stars isn't like spotting a new island on a map. You can't just point a telescope and see them sitting there. These worlds are too far away, too faint, drowned out by the light of the stars they orbit. So astronomers have to get clever. They watch for shadows, for wobbles, for tiny hints that something invisible is tugging at a star or passing in front of it. The method that caught this planet is called the transit method. Now imagine a planet crossing between that star and us here on Earth. For a brief moment, the planet blocks a sliver of the star's light. The star dims just a little, but enough for sensitive instruments to notice. If you watch long enough and that dip happens again at regular intervals, you know a planet is there. You can measure how long the dip lasts, how deep it goes, and from that figure out the planet's size and how far it orbits from its star. NASA's Kepler Space Telescope, launched in 2009 and retired in 2018, spent years doing exactly this. Specifically, this discovery came from Kepler's extended second mission, known as K2, which monitored a broader range of stars after the original mission concluded. Its job was simple but exhausting. Catch every flicker, every dimming, every hint of a planet passing by. The data it collected is still being analysed today, and that's where this discovery came from, not from a new mission, but from a careful look back at archived data. The study was led by Alexander Venner, a researcher at the Max Planck Institute for Astronomy in Germany, and published in January 2026 in the astrophysical journal Letters, one of the leading journals in planetary science. When the team spotted the signal for this planet, they knew immediately it was worth a second look. The star was the right type, stable, sun-like, not prone to violent outbursts that could strip away a planet's atmosphere. The dip in light suggested a planet roughly Earth-sized, not a giant, not a tiny rock, something in between. And the timing of the transit indicated an orbital period that placed the planet at a distance from its star where temperatures might allow for liquid water. That last part is critical. In the search for life, water is the key. Life as we know it requires liquid water to survive. Too close to a star and water boils away. Too far and it freezes solid. There's a sweet spot around every star called the habitable zone, where conditions might be just right. This planet's orbit puts it near that zone, not perfectly centered, but close enough to make scientists pay attention. Like all major discoveries, this one goes through a careful verification process. The entire discovery so far rests on a single transit, one instance of the planet's shadow crossing its star's face over the course of 10 hours. That single detection was unusually precise. But scientists need to see it repeat before they can call it confirmed. You need multiple observations. You need to see that shadow cross the star more than once, proving the pattern repeats. With this discovery, the team has strong evidence, but not yet the final confirmation. Follow-up observations may come from NASA's TESS satellite, the Transiting Exoplanet Survey satellite, which is currently the main workhorse for planet detection, or from the European Space Agency's CHEOPS satellite. Both are capable of catching the next transit if and when it occurs. If they see it, the planet moves from candidate to confirmed. If they don't, the mystery deepens. This waiting period requires patience from researchers. But that's how science works. Science moves on patience and verification, making sure the evidence holds up before any conclusions are drawn. What makes this candidate so compelling, even before confirmation, is how well it fits the profile we've been searching for. Out of thousands of planets discovered so far, most fall into categories that don't match Earth. Hot Jupiters, massive gas giants orbiting close to their stars, ice worlds far from any warmth, super-Earths that are rocky but much larger than our planet, with crushing gravity and thick atmospheres we don't fully understand. Finding something that mirrors Earth in size, orbit, and star type is rare. Rare enough that each one becomes a headline, and there's another advantage this planet has. Its star is bright. Brightness matters because the brighter the star, the easier it is to study any planets around it. When future telescopes look at this system, they'll have enough light to work with. They can analyze the starlight filtering through the planet's atmosphere, if it has one, and search for chemical signatures, oxygen, methane, water vapor, gases that might hint at life, or at least at conditions where life could take hold. The discovery process also highlights something beautiful about modern astronomy. We're not just finding planets anymore, we're finding worlds we can actually study in detail. Worlds where we can ask real questions and get real answers. Does this planet have clouds, seasons, weather patterns? Is its surface ice or rock or something in between? We're moving from simply knowing these places exist to understanding what they're really like. But before we get too far ahead, we need to talk about what makes this planet look so much like Earth. What are the specific similarities that have everyone buzzing? And just as importantly, where does it differ? Because as much as this world mirrors home, it's not a perfect copy. There are surprises hidden in the data, and some of them challenge what we thought we knew about where life can thrive. Let's break down the details that make this discovery so special. When scientists say a planet looks like Earth, they're talking about a checklist. Not every world can pass it. Most fall short in one category or another, but this planet, it ticks more boxes than almost anything we've found before, and that's why it's grabbing attention. Start with size. This isn't a massive super-Earth with gravity that would crush you. It's not a tiny rock with no chance of holding onto an atmosphere. Estimates suggest the planet is close to Earth in size. If it has a similar density, surface gravity might be comparable to what we experience here. That matters because size determines a lot. Whether a planet can keep gases from escaping into space, whether it can sustain geological activity that recycles nutrients, whether it can support the kind of processes that might lead to life. Then there's the orbit. This planet's orbital period is estimated to be roughly similar to Earth's year, though the exact length depends on confirmation data. Not a few days like planets hugging close. not decades like distant ice worlds. A year. That familiar rhythm. It means the planet gets a steady dose of starlight, spread out over time, creating the potential for stable seasons, stable temperatures, the kind of consistency that life needs to get a foothold and survive. The star itself is an important part of the story. It is slightly cooler and dimmer than our Sun, but unlike red dwarfs, which can flare unpredictably and bombard nearby planets with radiation, this star is calm and consistent. It has been shining steadily long enough for planets to form, cool down, and potentially develop complex environments. Together, these three factors give this planet what astronomers call an Earth analog profile. The closest thing to a twin our solar system has ever had a reason to study seriously. A world that, from a distance, mirrors the basic setup of our home. It's the kind of planet we've been dreaming about since we first started looking beyond our solar system. But there's more to the story. Scientists aren't just excited about what this planet is, they're excited about what it could have. The location of its orbit suggests the planet sits in or near the habitable zone. That's the region around a star where temperatures allow liquid water to exist on a planet's surface. Too close, and the heat boils oceans away. Too far, and everything freezes into ice. This planet threads that needle. Now, being in the habitable zone doesn't guarantee water. It doesn't guarantee life. It simply means the conditions are right for water to stay liquid if it's there. And water is everything. Every form of life we know depends on it. Water is the solvent where chemistry happens, where molecules meet and react and build the complex structures that lead to cells, organisms, ecosystems. Without water, the chances of life drop to nearly zero. So when researchers look at this planet and see it sitting right where water could flow, imaginations start running. Scientists want to know whether conditions could support liquid water on the surface, including stable weather patterns or active water cycles. These are genuine scientific questions that future observations may be able to address. And here's where the discovery gets even more interesting. The planet's star is close enough to us that we can study it in detail. Not next door, but near enough that light from the system reaches us clearly. That means when next-generation telescopes come online, they'll be able to point at this world and gather real data. They'll watch the starlight pass through the planet's atmosphere during a transit, looking for absorption lines that reveal what gases are present. Oxygen, carbon dioxide, methane, water vapor, each gas leaves a fingerprint. By reading those fingerprints, scientists can start to build a picture of what this world is really like. If they detect oxygen, that's a clue. Oxygen is reactive. It doesn't stick around in an atmosphere unless something is constantly replenishing it. On Earth, photosynthetic life, including plants and algae, constantly replenishes oxygen. Detecting large amounts of free oxygen on another planet would be a strong signal worth investigating further. But even without life, this planet could teach us so much. How do Earth-sized worlds form around Sun-like stars? What determines whether they stay warm or freeze over? How common are planets with the right conditions? And what does that tell us about our chances of finding life somewhere out there? Every new world we study adds a piece to the puzzle. While this planet shares key features with Earth, there are still details scientists want to fill in before they have the complete picture. It looks like Earth in the ways we can measure from afar, but we don't yet know the full story. Does it have a thick atmosphere or a thin one? Is its surface covered in water, ice, or dry rock? Does it have a magnetic field to protect it from radiation? These are the details that separate a true twin from a distant cousin. And there's one more thing. The data suggests this planet might be sitting right on the edge of the habitable zone, not comfortably in the center. That edge placement introduces uncertainty. It could mean the planet is warm enough for liquid water, or it could mean it's just a bit too cold to support liquid water on the surface. The truth is, we don't know yet. The research team estimates roughly a 40 to 51% chance the planet falls within some definition of the habitable zone, and about an equal chance it falls just outside it entirely. Those are genuinely uncertain odds, which is exactly why follow-up observations matter so much. That's what makes this so gripping. We're standing at a moment where the next observations could reveal something extraordinary, or remind us how rare truly Earth-like conditions might be. Either outcome will teach us something profound, and that's why scientists are so eager to point every available telescope at this system. They want answers. We all do. But before we get lost in the excitement, we need to confront the challenges. Because as much as this planet looks like home, there are real limitations that make this discovery more complex than it first appears. And those realities are what we'll explore next. Here's where the story takes a turn. As much as this planet checks the right boxes, there's a catch, and it's a big one. The planet sits at the outer edge of the habitable zone, not deep inside where conditions are comfortable, not in the sweet spot, it's on the border, and that border placement changes everything. Earth sits comfortably in the Sun's habitable zone. Venus is too close, baking under a runaway greenhouse effect. Mars is too far, cold and dry with only frozen water beneath its surface. The difference between these worlds shows how narrow the margin is. A little closer or a little farther, and you get wildly different outcomes. This newly discovered planet, it's closer to Mars's situation than Earth's. Scientists estimate that without a thick atmosphere, surface temperatures on this planet could drop to around minus 90 degrees Fahrenheit, colder than the average surface of Mars. Ice would dominate, locking away any water and making it unavailable for life as we know it. The planet receives less than a third of the heat and light that Earth gets from the Sun, which is why atmosphere becomes such a critical factor in determining whether any warmth can survive on the surface. That's an important point to keep in mind. We want this planet to be Earth's twin, to show us that our kind of world isn't unique. But the data doesn't promise that. It suggests something more complex, a world that could go either way depending on factors we can't yet measure. The team has seen the transit signal, but confirmation requires multiple observations. Other telescopes need to watch the star and catch the planet crossing again. Until that happens, there's always a chance the signal could be something else. A quirk in the data, a background object, an error. It's unlikely, given how strong and clear the signal appears, but science demands caution. That's important. We're not jumping to conclusions. We're following the trail of evidence, knowing that the picture could shift as more information comes in, but let's assume the planet is real and focus on the cold truth. If the surface is frozen, does that rule out life? Not necessarily. And here's why. Temperature isn't the only factor. Atmosphere plays a massive role. A thick atmosphere can trap heat, creating a greenhouse effect that warms the surface. Venus is extremely hot partly because of its proximity to the Sun, but mainly because its thick atmosphere creates an intense greenhouse effect that traps heat. The same principle works in reverse. A planet far from its star can still be warm enough for liquid water if it has the right atmospheric blanket. Scientists have run models for this planet testing different atmospheric scenarios. If it has a thick atmosphere rich in greenhouse gases like carbon dioxide, methane or water vapor, the surface could be much warmer than expected. Warm enough for rivers, warm enough for seas. The calculations show it's possible. Not guaranteed, but possible. And that's enough to keep hope alive. There's another twist. Even if the surface is frozen, life might exist beneath the ice. We see this on some of the moons in our own solar system. Europa, one of Jupiter's moons, likely has a liquid ocean beneath its icy surface kept warm by tidal forces. Enceladus, a moon of Saturn, ejects water vapor from what scientists believe is a subsurface ocean. If life can thrive in those hidden seas, why not on a frozen planet orbiting a distant star? Of course, studying life under ice is far harder than studying life on a surface with open water. But the point is, cold doesn't mean dead. It means we have to look harder, think more creatively, and accept that life might not always look the way we expect. Still, the uncertainty is frustrating. We want definitive answers. We want to know if this planet is warm or cold, wet or dry, alive or barren. But the truth is, we're working with limited data. We've seen a shadow. We've measured a size and an orbit. Everything else, atmosphere, temperature, water, life, is educated guesswork until we can point more advanced telescopes at this world and gather real observations. That's the nature of discovery at this scale. We find clues, we build models, we make predictions, then we wait for the technology to catch up and give us the tools to know for sure. It's a slow and painstaking process, but it's the only reliable way to reach the truth. And here's something to consider. Even if this planet turns out to be too cold for life, the discovery still matters. It shows us where planets form. It teaches us how common Earth-sized worlds are around sun-like stars. It helps us refine our search strategies so we know where to look next. Every candidate, whether it pans out or not, moves us closer to finding the real thing. But let's not give up on this world just yet. The cold truth is balanced by genuine possibility. The edge of the habitable zone isn't a death sentence, it's a challenge. And if there's one thing we've learned from studying life on Earth, it's that life is good at meeting challenges. Life finds a way. It adapts. It survives in places we thought were impossible: deep ocean vents, frozen Antarctic lakes, acidic springs, radiation-soaked rocks. So when we look at this planet on the edge, we shouldn't see a failure. We should see a question, a test case, a chance to learn whether the habitable zone is as rigid as we think, or whether life's boundaries stretch farther than we imagined. The next step is to dig deeper into what this planet might actually have. What would it take for life to survive there? What conditions would need to be met? And why are scientists calling this one of the best places to search, even with all the uncertainty? That's where the real hope lies, in the details of water, atmosphere, and the tools we'll use to uncover the truth. When we talk about life beyond Earth, we always come back to water. Not because we lack imagination, but because water works. It's the universal solvent, the medium where chemistry comes alive. Every biological process we know of depends on water. Without it, life as we understand it cannot function. So the first question for any planet is simple: does it have water? And more importantly, is that water liquid? Because ice doesn't help much. Ice is stable, locked, inert. Life needs movement. It needs molecules colliding, reacting, building complexity. That happens in liquid water. For this planet, the answer isn't clear yet. We can't directly see oceans or lakes from here. What we can do is look at the conditions and make educated guesses. The planet orbits in or near the habitable zone. That means temperatures could support liquid water if other factors align. But what are those factors? Atmosphere is the big one. A planet without an atmosphere is doomed. It doesn't matter if it's the right distance from its star. Without air to trap heat and regulate temperature, the surface becomes a frozen wasteland at night and a scorched desert by day. Mars shows us this. It has a very thin atmosphere, and even though it sits at the outer edge of the Sun's habitable zone, its surface is cold and dry. But if this planet has a thick atmosphere, everything changes. Greenhouse gases trap warmth, clouds reflect and redistribute heat, winds carry moisture. Suddenly, you have a dynamic system where water can cycle, evaporating, condensing, falling as rain, carving rivers, filling seas. That's the kind of environment where life has a shot. Scientists have modelled different atmospheric scenarios for this world. If the atmosphere is mostly nitrogen and oxygen, like Earth's, the surface would likely be cold. Nitrogen and oxygen aren't strong greenhouse gases. They let heat escape. But if the atmosphere is rich in carbon dioxide or methane, the greenhouse effect kicks in. Surface temperatures could rise above freezing, allowing liquid water to pool on the surface. Water vapor itself acts as a greenhouse gas. If the planet has even a little warmth, ice could melt into vapor, which traps more heat, which melts more ice, which creates more vapor. It's a feedback loop. That loop could push the planet from frozen to habitable. Or it could have happened long ago, leaving behind a stable, watery world. Now, here's where it gets exciting. Scientists have flagged this planet as a strong candidate for follow-up observations with more powerful telescopes. Why? Because the star is bright enough, and the planet's orbit is positioned such that when next-generation telescopes come online, they'll be able to analyze the atmosphere in detail. They'll watch the starlight pass through the planet's air during a transit, and the gases will absorb specific wavelengths of light. By measuring which wavelengths are missing, scientists can identify what gases are present. If they find water vapor, that's a good sign. It means water exists on the planet, likely cycling between surface and atmosphere. If they find oxygen in large amounts, that's a huge clue. Free oxygen breaks down quickly in an atmosphere unless something keeps producing it. On Earth, plants and microbes do that job through photosynthesis. Finding large amounts of oxygen on another planet would be a strong clue worth investigating, though scientists would still need to rule out non-biological sources. Methane is another interesting gas. Methane breaks down quickly in the presence of ultraviolet light. If there's methane in the atmosphere, something must be replenishing it. That something could be volcanic activity, or it could be life. On Earth, microbes produce methane as a byproduct. Detecting methane alongside other gases like oxygen or carbon dioxide could point toward biological processes. But let's be honest, finding life signs won't be easy. The signals are subtle, atmospheres are complex. A gas that looks like a life sign could also have a non-biological explanation. Scientists will need to rule out false positives, study the planet over time, gather as much data as possible before making bold claims. Still, the possibility is enough to drive the search forward, and this planet is one of the best candidates we have. Not because it's perfect, it's not, but because it's accessible, We can study it. We can point our best instruments at it and get answers. That's rare. Most exoplanets are too far, too faint, or orbit stars too dim for detailed analysis. This one is different. There's also the question of habitability over time. A planet's atmosphere doesn't stay the same forever. It evolves. Volcanoes pump gases into the air. Solar wind strips lighter molecules away. Life, if it exists, changes the chemistry. Understanding how these processes work on another world will help us understand how common habitable planets really are. How delicate is the balance? How many things have to go right? How much variation is there in the recipe? Every world we study teaches us something new about the conditions that allow life to emerge and survive. On Earth, life has been microbial for most of the planet's history. Complex life, animals, plants, fungi, are recent arrivals. If this distant planet has life, it's probably simple. If life exists there, it would most likely be simple, such as microbes or bacteria, rather than complex organisms. Detecting that kind of life requires looking for subtle chemical imbalances, patterns that don't fit non-living processes. That's why the search is so methodical. Scientists aren't expecting little green creatures, they're expecting data. They look for detailed light readings, specific gaps in the light spectrum, and tiny deviations that hint at something more. And if they find those hints, they'll study them for years, testing every alternative explanation before concluding that life is the answer. But even the search itself is thrilling. We're living in the first era of human history where we can actually look for life beyond Earth and have a real chance of finding it. It means every new planet we discover, every spectrum we analyze, every model we run, brings us closer to answering one of the oldest questions our species has ever asked. Are we alone? This planet, HD 137010b, with its position near the outer edge of the habitable zone, its Earth-like size, and its stable though somewhat cooler star represents one of our best shots at finding out. It's not the only candidate and nothing is guaranteed, but it represents a genuine opportunity. And that's worth every telescope, every calculation, every hour spent carefully analysing data. The hope isn't just about finding life somewhere else. It's about understanding life itself, where it comes from, what it needs, how rare or common it might be, and ultimately what it means for us here on Earth, looking up at the stars and wondering if someone or something is looking back. So the life question remains open. Water could be there. The atmosphere could make it work. Scientists check the chemistry for signs of life. Or it could all be barren, a reminder that even planets that look right can fall short. Either way, we're about to learn something profound, and that's what drives the search forward. This discovery isn't just another headline. It's not just a checkbox in a catalogue of distant worlds. This planet matters because it changes how we see the universe and our place in it. For most of human history, we assumed Earth was unique, the only world with life, the only place where conditions aligned perfectly for biology to flourish. Even as we learned about other planets in our solar system, none of them looked like home. Mars was cold and dead. Venus was a hellish furnace. The gas giants had no solid ground. We seemed alone, a cosmic accident on a rare and precious world. Then we started finding planets around other stars, thousands of them, and slowly the picture shifted. We weren't unique in having a planet. We weren't even unique in having a rocky planet. The galaxy is filled with worlds. But here's the thing. Most of those worlds are nothing like Earth. They're too big, too hot, too close to unstable stars. Finding planets is easy now. Finding planets like ours, that's still hard. This candidate represents a step forward. It shows us that sun-like stars can host Earth-sized planets in orbits that might allow water and life. That conclusion comes from real observations, not guesswork. And the more examples we find, the more we realize that our kind of world isn't a fluke. It's a possibility that repeats across the galaxy. Think about what that means. Every sun-like star in the night sky could have a planet like this. Maybe not all of them, maybe not most, but some. And if some of them have the right conditions. And if life can take hold the way it did here, then life could potentially exist in multiple locations across the universe. Not in every system, not on every world, but scattered through the stars, hidden in places we haven't looked yet. That changes everything. It means we're not alone, not in the sense that life is rare and precious, but in the sense that life may arise more commonly than we once thought, if the right conditions are present. It means the story of life isn't just our story. It's a universal story, playing out on countless worlds, each one unique but connected by the same chemistry, the same physics, the same rules. And even if this particular planet turns out to be lifeless, the fact that it exists matters. It tells us where to look. It refines our understanding of what makes a planet habitable. It shows us that Earth analogues are out there, waiting to be found. Every candidate we study, whether it has life or not, teaches us something about the conditions that allow worlds like ours to form and survive. There's another reason this discovery resonates. It taps into something deeply human, the desire to know we're not alone. We've asked that question for as long as we've been able to ask questions. We've looked up at the stars and wondered if someone else was looking back. For the first time in history, we have the tools to find out, and planets like this are where we start. But beyond the search for life, this discovery also challenges us to think differently about Earth. If other worlds like ours exist, then our home isn't as special as we once thought. That might sound disappointing, but it's actually liberating. It means the principles that make Earth habitable, stable star, right distance, liquid water, protective atmosphere, aren't miraculous. They're reproducible. And if they're reproducible, we can study them. We can understand them. We can maybe even recognize them before life emerges, giving us a chance to watch biology begin somewhere else. This also has implications for the future. As humanity looks outward, as we think about becoming a spacefaring species, knowing where habitable worlds are located becomes crucial. Not because we'll travel there anytime soon, the distances are too vast, but because these discoveries map the possibilities. They show us what's out there. They give us targets for future generations to study, visit, or communicate with if technology ever catches up to our dreams. And there's a philosophical dimension too. Finding another world like Earth forces us to reconsider our responsibility to our own planet. If life-friendly worlds are rare, even if they're not unique, then Earth becomes more precious. It's not the only one, but it's ours. It's the one we evolved on, the one we're adapted to. Seeing another world that could have life makes us realize how fragile and valuable our home truly is. The search for planets like this also drives technology forward. The telescopes we're building, the techniques we're developing, the data analysis methods we're refining, all of it pushes the boundaries of what's possible. And that technology doesn't just serve astronomy, it filters into other fields, better sensors, better optics, better computing. The benefits ripple outward, improving our ability to tackle challenges here on Earth. So when we say this planet matters, we're talking about more than just one distant world. We're talking about a shift in perspective, a new chapter in the human story, a moment where we move from wondering if other Earths exist to studying them, analysing them, learning from them. And the timing couldn't be better. We're on the verge of launching telescopes powerful enough to see into the atmospheres of distant planets. We're refining models that predict habitability. We're building instruments that can detect the faintest chemical signatures. Within the next several years, we may begin to get clearer answers to some of these questions. That's why this discovery feels different. It represents a step forward in our understanding of how common Earth-like planets may be, and brings us closer to answering whether life exists beyond Earth. We're at an early but important point in this kind of research, and this planet is one of the best candidates we currently have for follow-up study. But the story doesn't end with discovery, it's just beginning. Because knowing a planet exists is one thing, understanding it is another, and the next steps in this journey are as important as the discovery itself. Let's talk about what happens now. So we've found this planet, or at least we've found strong evidence it's there. Now what? How do we go from a candidate to confirmed discovery? And once it's confirmed, how do we learn more? The next steps are as crucial as the discovery itself, and they're already in motion. First, confirmation. Right now, this planet is a candidate, and the team has detected the transit signal, the dip in starlight that suggests a planet crossing in front of its star. But to confirm the planet is real, other telescopes need to observe the same star and catch that same dip happening again. Timing is everything. Transits are predictable. If the planet is real, it will cross in front of the star at regular intervals based on its orbital period. Astronomers are scheduling follow-up observations using ground-based telescopes and other space observatories. They'll watch the star at the times when the transit should occur. If they see the dip, the planet is confirmed. If they don't, the signal might have been something else: instrument noise, a background star, or a rare event that won't repeat. Confirmation could take months or even years, depending on the planet's orbit and telescope availability. Once confirmed, the real work begins. The next goal is to study the planet's atmosphere. This is where things get exciting. When a planet transits its star, some of the starlight passes through the planet's atmosphere before reaching us. Gases in that atmosphere absorb specific wavelengths of light, creating a unique fingerprint. By analysing that fingerprint, scientists can identify which gases are present. To do this, we need more powerful telescopes. Ground-based observatories can help, but space telescopes offer the best results because they avoid interference from Earth's atmosphere. New missions are being planned specifically for this kind of work. Instruments designed to capture faint signals and separate them into detailed spectra. These tools will allow scientists to measure the atmospheric composition of planets like this one. What are they looking for? Water vapor is high on the list. Detecting water in the atmosphere would confirm that water exists on the planet, likely in the form of oceans, lakes, or atmospheric moisture. Carbon dioxide is another target. It's a common gas and a strong greenhouse contributor, so finding it would help scientists model the planet's temperature and climate. Oxygen and methane remain the most significant gases to look for, as both can point toward biological activity. Finding them in large quantities would be a strong signal worth investigating carefully. Methane breaks down quickly in an atmosphere, so if it is present, something must be constantly replenishing it, either volcanic processes or potentially living organisms. But detecting these gases won't be easy. The signals are faint. The planet's atmosphere is thin compared to the bright light of the star. Separating the two requires incredibly precise measurements. Scientists will need multiple observations taken over time to build confidence in their findings. They'll also need to rule out other explanations. A gas that looks like a life sign could also come from volcanic activity or chemical reactions in the atmosphere. Timing matters too. The next generation of space telescopes is coming online soon. These instruments will have the sensitivity and resolution needed to study planets like this in detail. The observations could start within the next few years, depending on the telescope's schedule and the planet's conformation status. It's a waiting game, but the payoff could be enormous. There are other questions scientists want to answer as well. Does the planet have a magnetic field? Magnetic fields protect atmospheres from being stripped away by the stream of charged particles that flow outward from a star, known as stellar wind. Earth's magnetic field is one reason we still have air to breathe. Detecting a magnetic field on a distant planet is challenging, but not impossible. Certain signatures in the star's behavior or the planet's interaction with stellar wind could provide clues. What about surface conditions? Can we tell if the planet has oceans, continents, ice caps? Direct imaging is still beyond our current technology for a planet this far away, but indirect methods can help. Analyzing reflected light from the planet, if we can capture enough of it, might reveal surface features. Ice reflects light differently than liquid water. Rock has its own signature. Vegetation, if it exists, would change the light in unique ways. These are long shots, but worth pursuing. And then there's the question of seasons and climate. Does the planet have an axial tilt like Earth? That slight lean in a planet's rotation that gives us our 4 seasons? How stable is its orbit? Are there moons that could influence tides or geological activity? Every detail adds to the picture. Every observation brings us closer to understanding what this world is really like. The ultimate goal is to build a complete profile, not just size and orbit, but atmosphere, temperature, surface, and chemistry. We want to know if this planet could support life as we know it, and if it can, we want to know if life is actually there. That's the dream. That's what drives the science forward. But even if the answer is no, even if this planet turns out to be barren, the search continues. This is just one candidate among many. Every year we find more. Every year our tools improve. Every year we get closer to answers that could significantly change how we understand our place in the universe. So what happens now? We watch, we wait, we gather data, and we prepare for the moment when the next observation comes in and we learn something new. The journey is far from over. In fact, it's just beginning. So here we are, standing at the edge of one of the biggest questions humanity has ever faced. Is there life beyond Earth? And could this planet, HD 137010b, circling a stable but somewhat cooler star 146 light-years away, sitting near the outer edge of the habitable zone, matching our home in size and orbit, be the place where we find the answer? We've covered a lot. We've talked about how they found it, what makes it special, the challenges it faces, and the hope that keeps scientists searching. We've explored the water question, the role of atmosphere, and the technology that will help us see this world more clearly. And we've looked at why this discovery matters not just for science, but for how we understand ourselves and our place in the cosmos. What's your reaction to this discovery? Do you think a planet like HD 137010b, sitting on the cold edge of the habitable zone, could still support some form of life? Drop your thoughts in the comments. We are living in the first period of human history where these questions can actually be investigated with real evidence, and that is worth taking a moment to think about. If this video sparked your curiosity, hit that like button. It helps more people discover these stories. And subscribe, turn that bell on, because this story is just starting. New telescopes are coming online, new data is being collected, and this story will continue to develop. I'll cover each significant update as it comes in. Thank you for watching. These are questions worth taking seriously, and it means something that you're curious about them. The universe is vast, and we're just beginning to explore it. But every discovery, every planet, every question brings us closer to understanding not just what's out there, but who we are.